Okay, so in chapter 14, we are going to start thinking about chemical kinetics. Okay? So chemical kinetics is basically studying the rates of reactions. Okay? And we also need to think about whether reactions are spontaneous or not. Do they happen without any influence? Sometimes a reaction can be spontaneous, but it doesn't necessarily mean that it's fast. So a good example of this is the reaction of the formation of ammonia gas Okay. So in this reaction, nitrogen from the atmosphere combines with hydrogen to form ammonia. But at 25 degrees Celsius, so room temperature, this essentially will not occur. Okay. So example, at 25 C and 1 atmosphere, this reaction does not happen. But you may have heard of the Haber process. Maybe not, but that's okay. So the Haber process is a really important reaction that allows us to make ammonia at relatively easy to access temperatures and pressures. And what it does is it uses an iron catalyst, okay, which helps to speed up the reaction. Okay, so we take a reaction that technically could happen, but it just doesn't happen very quickly. This is the formation of ammonia. It doesn't happen very quickly at 25 C, 1 atmosphere. We combine these gases in the presence of an iron catalyst, and it then occurs very quickly. And that process is called the Haber process. I mentioned last time we were going to miss talking about war criminals. That Fritz Haber made chemical warfare in World War I. It's got an interesting story. If you have time to and you want to do some reading, I'm sure his Wikipedia page is quite fun. So, yeah, that's this process. So again, this is a spontaneous reaction. It just doesn't happen very fast. At room temperature, we add a catalyst, we make it go. Okay. So there are a number of factors that affect the reaction rate. And a lot of these go back to kinetic molecular theory. Which you may have encountered in your study of gases in previous coursework. Right? Essentially what kinetic molecular theory says is that particles must move and interact with each other, collide, in order for a reaction to take place. So for the reaction of ammonia to form, we need to have a nitrogen molecule, combine with a hydrogen molecule, collide, and the reaction takes place. So using that chemical intuition, okay, which of these factors is going to make a rate faster? Take a look at those, make some quick guesses, and then we'll talk about each of them. Feel free to talk to your neighbors. All right, let's bring it back in. Thank you. What do we think about concentration of reactions? What's just going to be higher, a high concentration or a low concentration? High, yeah. So If we're thinking about molecules colliding, if you have more of them in a container, the better chances they are of colliding. Okay, so a higher concentration, more in a container, faster rate. What about temperature? High, yeah. So again, and we're going to think more about this, but with kinetic molecular theory, if we can make molecules move faster by giving them energy, and one way to do that is by applying heat, so increasing the temperature. And again, making the molecules move faster makes them collide more frequently, and then we end up with the faster rate. What about physical state? What about liquid? We got a lot of gas. What do you think about liquids? Yeah, okay. So this one's kind of tricky because liquid and gas are approximately equal, all right? Now, if you have, and we're thinking about liquids, this could be pure liquids, two pure liquids combining, but it could also be solutions. Solids generally don't react very quickly, okay? But if you think about two solutions that have reactants in them and you combine them, often that reaction can occur very quickly, okay? You just need to have a way for those molecules to collide. And things are moving fairly quickly in a liquid or in a solution phase. What about particle size? Small, yeah. So small particles tend to collide or tend to react faster. This is sort of akin to like if you crush up a powder and, well, I shouldn't talk about drugs. A drug that you're supposed to take, a prescribed drug, and you crush that, it actually can react in your body much faster than if you take it in the pill form. Oh, those capsules, you know, have you ever taken apart a capsule and it has all these little pellets in it? You're supposed to take it as the capsule, not as the little pellets, because of that rate of reaction. Okay, and then we talked about the presence of a catalyst. That also can increase the rate of the reaction. So let's assume these three boxes contain our reaction vessels. And they contain two reactants, A and B. We can say that the blue spheres are A and the red spheres are B. Which of these is going to react the fastest, based on what we just talked about? I may say A. I may say B. I may say C. Okay, cool. Yeah, so in B we have a higher concentration of reactants and they're in the gas phase, okay? Higher than C, higher concentration than C. So that's why B would react faster than C, okay? So, all right, B has a higher concentration than C. That looks almost like I wrote that. And then B and C would be faster than A because A is a solid. All right. So we need to be thinking about what reaction rate really means. Okay? So you all, I assume, are familiar with riding in a car or some sort of vehicle. If you're driving, you're watching the speed limit on your dashboard, you see at a particular instance, you're on the highway, you're going 70 miles an hour. And that's miles per hour, so those are our units. Now let's say you're driving from Columbus to Cleveland. It takes about 2 hours to get there. And you've figured that over, how many miles is it to Cleveland? Someone wants to know this, right? What is it? 170? So, yeah, it's 170 miles to Cleveland. Then if you figure out how long it takes you to get there, 2 hours, you can divide your miles by the amount of time and figure out your average speed. So we're going to be thinking about two of these things in terms of reaction rates. We're going to be thinking about instantaneous rate, or instantaneous speed, the number on the dashboard, and then the overall rate, and that is sort of more how long, or what is your average, okay? So what this graph is trying to show, each of these black points, we can measure an instantaneous rate, okay? When on our x-axis we have time, on our y-axis we have concentration of reactant, and you'll notice that that formula is written inside brackets. C4H9Cl in brackets. The brackets symbolize this is concentration. Okay, we're going to use that a lot this semester if you haven't seen that before. So this reactant is called chlorobutane. Not something you would need to know, but just so it has a name. Chlorobutane reacts with water to form butanol and HCl. Okay? So we have concentration of the reactant chlorobutane on the y-axis and time on the x-axis. At any particular point along this curve, we can determine an instantaneous rate, right? And where am I? We can also look at a reaction rate in terms of determining the change in concentration of a reactant or a product over time. And so that would look something like this. Change in the chlorobutane concentration over the change in time. And that's what we're trying to show within these triangles. Okay? Concentration change, time change, and we can figure out the rate. All right. Now we won't be doing tangents of graphs and things like that to do that, but that is where this is coming from. The other thing I want to point out is that rates are always going to be given as positive numbers. Okay? But we are going to use a negative sign occasionally, and we just need to keep in mind what that's going to mean, and I'll show you that on the next slide. All right. The rates are going to be given as positive numbers. You're also going to see that we're going to see different types of plots, okay? And as we get into further into the chapter, we're going to talk about what those lines mean in those plots. They tell us something about the reaction. For now, let's take a look at this plot. We have the concentration of something, x, on our y-axis, and time on the x-axis. And you'll see that with time, as time increases, the concentration increases. Okay? Based on that, which of these four possible things is true? Is it A, X is a reactant and the reaction rate is speeding up? X is a reactant and the reaction rate is slowing down? X is a product and the reaction rate is speeding up, or the opposite, X is a product and slowing down? So just think about what you would expect based on that previous slide we saw. Take a guess here. Okay, let's break this into two parts. Is X a reactant or a product? They're both, so I'll let you know. It is a product. the concentration is increasing with time. So that means that X is being formed during the reaction. So if X is being formed, it has to be a product. Okay? So we're either down to C or D. So X is a product. Again, the concentration is increasing with time. For me, and maybe this isn't true for you, the second part is a little bit harder to see. Okay? And that is whether the reaction rate is speeding up or slowing down. And so what I've tried to do here is draw vertical lines on our x-axis, and they're supposed to be evenly spaced. I did what I could. And so what we can do then is look at the change in concentration over the same unit of time early in the reaction and later in the reaction. So I'm going to take two lines early in the reaction, and we've gone this much vertically in terms of concentration change. Okay. And then if I take two lines later in the reaction, let me change that. Nope, let's do blue. And look at this vertical change here, it's actually much smaller than that first part of the reaction, right? So this vertical part is much larger than this vertical part. And that's over the same period of time. So let's say, for instance, this number corresponds to this what I would say maybe this height is about a third of this height. Agree with that somewhere in there? We're going to make up numbers now. I like doing this. This is how I approach this. This may not be your approach, but this is what I like to do. So let's say that this height, this first early part of the graph, we're going to call that 9 units over some amount time. Okay, 9 units. We just made that up. Okay, made up number. Okay. In the later half of the reaction, this height is definitely smaller than this height. I think it's about a third of this height. Could be a half. But I made it 9 because I wanted it to be a third. A third of 9 is 3 over some amount of time. And so what this is telling us, if our time t is 1 second, early on in the reaction, we're going 9 concentration units per second. Later on in the reaction, we're going 3 concentration units per second. So the reaction rate is slowing down. So if when you looked at this graph, the way this graph curves, if that didn't quickly occur to you that this is a rate slowing, that the concentration isn't increasing as fast as early on, you can kind of apply these little mathematical, manipulations to kind of make it make sense. Does that make sense? Okay. Cool. So reaction rate is slowing down, and this is a product. All right. So let's get some stoichiometry involved. Sorry for the blurriness here. Let's say we have our chlorobutane reaction, C4H9Cl, reacting with water to form butanol and HCl. Okay? We are going to define the rate as the change in concentration over the change in time, right? For the reactant is going away. So we put a negative sign in front of it. That signifies that the concentration is going down. Okay? Because we go back to my favorite type of calculation. The change in concentration is equal to the concentration final minus initial. Okay? I. Final minus initial. If the reactant is going away, the final concentration is going to be less than the initial concentration. And so we end up with a negative value. Okay. So we put a negative sign in this equation to account for that. Okay. Now, on the right-hand side of that equation, of this, we have the concentration of the product butanol over the change in time, and this has a positive value. These are all related by stoichiometry, and this is not the best example, but we're going to get to a better one. Everything has a stoichiometric coefficient of 1. Okay? So they're all 1 to 1 to 1. And we can even include how the change in water is going to look over time, as well as the HCl. So water is another reactant. Okay? So if we want to relate it to the rate of change of the chlorobutane, it's going to be equal to minus the change in the concentration of H2O over the change in time. And for our other product, HCl, it's going to be equal to the change in concentration of HCl over the change in time. So what this says, what this should say, as you look at this equation, is that if the rate of the reactant chlorobutane going away is 3 molar per second, then the rate of formation of butanol is 3 molar per second. The rate of water going away is minus 3 molars per second. And the rate of formation of HCl is 3 molar per second. So they're all 1 to 1 to 1. Okay? They're all equal to the same number. Okay? So we can relate any reactant or product. Okay. So again, remember, rate is always going to be a positive number. If you're working on problems and it asks for the magnitude of the rate, let's say you're looking at the rate, what is the magnitude of the rate of decay of a reactant? It's actually looking for the positive number, because magnitude is ignoring the sign. Does that make sense? So if you see that term, just you ignore the sign if it's negative. Okay, so as I said, we can relate the rate of any reactant and product, and we need to take account the stoichiometry of the reactant. And the way we do that is with this really important equation. Okay, so this rate is for the reaction that is A plus B yields C plus D, where lowercase a, lowercase b, lowercase c, and lowercase d, those are all the stoichiometric coefficients. So when we have our rate of decay of reactant A, it's going to be equal to minus 1 over its stoichiometric coefficient times its change in concentration over the change in time. So when you're thinking about relating rates for reactants and products, remember that you must include the stoichiometric coefficients. And for me, I'm always thinking, okay, they're 1 over the stoichiometric coefficient. Okay. And I can't remember if that equation is given on the exam. I don't think it is. So that is something you're going to want to remember. Questions on that or anything? Okay. All right, so let's practice this a little bit. Okay, so as we said, we can express a reaction's rate in terms of any product or reactant. So here we're going to have the reaction 2HI gas forms H2 gas and I2 gas. Okay, we're forming hydrogen and iodine. Yeah. At a certain point in time, H2 is being produced at a rate of 3 moles per liter per second. Okay? See our units. Its units are in concentration over time. At what rate is I2 being produced? Okay? So we can relate the rate of formation of I2 or H2 to that of I2. And that is shown here in this equation. The stoichiometric coefficients are 1. So we essentially have 1 over 1 relating those. Or 1, yeah. Okay? So the rate that I2 is being produced is the exact same as the rate of H2 being produced. 3 moles per liter per second. All right. The slightly trickier question then is what is the rate of HI being consumed? And I'll let you work on that for a minute. You can talk to your neighbors. Okay, so I've set up an equation where I'm relating the rate of decay of the reactant, HI, to that of the rate of formation of H2. Okay, and I do 1 over the stoichiometric coefficient, 1 over 2, 2 for here, from here. Change in concentration of HI over change in time equals 1 over the stoichiometric coefficient. Again, this is 1. I usually leave it off. Times the change in concentration of H2 over the change in time. And now we're solving for delta HI over delta T. So I'm going to multiply both sides by 2, minus 2, sure. This is where we're going to leave off that minus sign, and you're going to get grumpy at me. I don't blame you. But we're going to say that all rates are positive. Okay? So we're going to have 2, in effect, essentially 2 times 3 mole per liter per second. So we get 6, but all rates are positive. So delta HI over delta T equals 6, not 66, moles per liter per second. Does that make sense? Questions on that? Okay. I think one of the things that is the hardest sort of conceptual part of the kinetics chapter is identifying what type of question is being asked when you get to a whole bunch of different types of questions. So this is when you know a rate, okay, and you're relating rates between reactants and products. You're going to have other rates and other things with concentration, and we're going to get to those soon. Any questions again before moving on? Again, sorry for the formatting. I do not know what's happening on this. This is NO2. Okay, so now here we're going to do one more problem like this. And here we're given actual time and concentration data. Okay, so here we have two nitrous dioxide forming two nitrogen monoxide and oxygen gas. So we want to first figure out the rate of appearance of oxygen. All right, so we know we have some data that are given in the table. We have concentration of nitrogen monoxide, and we have time. So we're going to be able to figure out the rate over this time period for NO. And over the same time period, what is the rate of appearance of oxygen? And then we're going to find the rate of disappearance of NO2. So I'm going to let you take a couple minutes and work on that one. So I'm going to also include over the same time period, just so there's no confusion. Okay. Apologize if that's not quite enough time, but I just kind of want to keep moving. So the first thing I want to do is actually determine the rate over this time period for the formation of nitrogen monoxide. And so I'm going to use the equation change in concentration of NO over change in time. And I'm just going to use the data from the table. And I'm going to do final minus initial. In terms of concentration, this is 0.0061 minus 0.0055. And in terms of time, this is 285 minus 215. And what do we get? 8.6 times 10 to the minus 6 moles per liter per second. Got that? Okay, cool. Okay, so that is the rate of formation of nitrogen monoxide over the time period of 215 to 285 seconds. Essentially, that's the average rate in that time. Okay? So then what is the rate of appearance of oxygen within this same time frame? Because we know this value, and because we can use the stoichiometry to make the relationships, we can do 1/2 concentration of NO over concentration of time equals 1 over 1 change in concentration of oxygen over change in time. Okay. And then we can plug in the value for change in NO over change in time and solve for change in O2 over change in time. So we're going to get 1/2 8.6 times 10 to the minus 6. Yeah, and get 4.3 times 10 to the minus 6 moles per liter per second. We're okay with that? Okay. The rate of disappearance of NO2. Okay, again, using the stoichiometry, I'm going to start with my product that we know, 1/2 concentration of NO over change in time equals minus 1/2 delta NO2 over change in time. We have a quick answer? Yeah. 8.6 times 10 to the minus 6 moles per liter per second. So you could work through the math if you wanted, but because the stoichiometry is the same for NO2 as it is for NO, you know that the rates are going to be the same. Okay, so we just basically pulled this number. That make sense? And even though there's a negative sign, rates are always positive. Okay. Questions? Okay, those are pretty straightforward, right? Good. Summary here. Reaction rates are expressed as changes in concentration per time, moles per liter per second. And usually what we see is that the rate slows down as the reaction proceeds. And when you go back and look at these slides, which I'm sure you're looking forward to doing, you can take a look at all of those lines in the plots, and you'll see that they start to flatten out. And so that means that the rate is slowing. And then there's a few other things here. Know that the stoichiometry is important and things like that. I'll let you read through that on your own. Okay. This slide leads us into our next batch of notes, which this would be a good time to grab them if you don't have the next set of slides from Carmen. But if we take a look at the reaction that we were just kind of studying with the reaction rates table, one thing to think about is reactions are reversible. So when we have enough products built up, those products can react together and reform reactants. So we have a forward reaction and have a reverse reaction. We're going to talk a whole lot more about this, basically the rest of the semester, starting with chapter 15. But so we need to think about how could the fact that once we have products, they could start forming reactants again. If you think about what that could mean, we could start seeing new reactants and measuring those, and that would mess up the rate of the reaction and all of that, right? So we need to think about only measuring the rate very early on in a reaction before we have any products that can form or can react and reform reactants. So we do a method of initial rates, and we use what we call rate laws. Okay. So this is basically the study of reaction rates before products have time to build up. All right, and so we're going to identify these rate laws.